Continuing here from page 46, roots of complex numbers. Now, de Moivre's theorem allows us to find a complex number to the power of n, so z to the power of n, if we're given the complex number z. Now, we know that if z equals r cis theta, which is cos theta plus I sine theta, and if n is an integer, then z to the power of n will be r to the power of n bracket cos n theta plus I sine n theta, or just that z to the power of n will be r to the power of n cis n theta. Now that's de Moivre's theorem. Now de Moivre's theorem provides us a method for finding the nth root of z to the power of n. That is, if you're given z to the power of n, you can find z, the roots of z to the power of n. So before we look at some examples, we need to look at the fundamental theorem of algebra, which is the number of roots of an equation is always equal to the degree of the equation. These roots may be real or complex single roots or multiple roots. So if we've got z to the power of 3 equals 1, it will have 3 roots because the number of roots equals the degree of the equation, and this equation has degree 3. Z to the power of 4 equals 16 will have 4 roots because this is degree 4. Z to the power of 5 equals 5 plus 12i will have 5 roots because this is an equation of degree 5. So looking at this first example, find the cube roots of 1. So we're trying to find the cube roots of 1, basically. Now, to do that, we really want to solve the equation z cubed is 1, because if z cubed is 1, then z will equal the cubed root of 1, okay? So if you're finding the cube roots of 1, which is that cube roots of 1, if z is the cube roots of 1, you're really finding you need to solve the equation z cubed is 1, because if you take cube root of both sides, z will be the cube root of 1. So we're solving z cubed equals 1. Let's start by letting z equal to r cis theta. Therefore z cubed equals r cubed cis 3 theta, according to de Moivre's theorem. Now what I'm also going to do, so I've written z cubed in terms using de Moivre's theorem, r cubed cis 3 theta. What I'm going to do, I'm going to rewrite 1 in mod arg form as well. So I know that 1 is equal to 1 times cos 0 plus I sine 0. Now what I'm going to do to help you with that, because that's sometimes a little bit hard to do, 1 is in here. 1 is here. Now what is the modulus of 1? So there's the origin. 1 is there. The modulus of 1 is 1, so therefore r is 1. But the argument of 1, of the point 1, is 0, because the argument, remember, is the direction from the positive x-axis going anti-clockwise, and the angle, if that is 1 there, and if this is if I draw the vector or whatever, then the argument here is 0, because we don't have any angle there for theta. Okay, it's 0. So 1 can be written as 1 cos 0 plus I sine 0, because remember it's 1 equals 1 cis 0, which is 1 cos 0 plus I sine 0. The other way you can look at this is using a cosine curve. Cos of 0 is 1 and sine of 0 is 0. Okay, so 1 times 1 plus sine 0 is 0. 1 times 1 is 1. So we're just expressing 1 in modulus argument form. Now, because this is now in modulus argument form, and so is that, we can equate left-hand side with right-hand side of this. So therefore, as we know z cubed equals 1, I can say that r cubed cis 3 theta equals 1 cos 0, or cos 0 plus I sine 0, Or I can just say r cubed cis 3 theta is 1 cis 0, rather than writing it out all this way. So I probably should have done that there and write that as 1 cis 0. So now I can equate, sorry you can't see that. So now equating moduli and arguments. So equating moduli and arguments. I've got that r cubed equals 1. And so therefore r is 1. Now r will be 1 since the modulus is always a real number. So since the modulus is a real number. And equating the arguments, we get that 3 theta here is equal to 0. However, it's equal to 0 plus 2 k pi, where k equals 0, 1, 2, 3, etc., where it's 0 or a positive integer. Now, the reason for that is if the argument is 0, the next time the argument is 0 is 2 pi further on, and the next time the argument is 0 is 2 pi, another multiple of 2 pi, etc. So that's why 3 theta, it's like we're giving the general solution here. So 3 theta equals 0 plus any multiples of 2 pi. And now dividing by 3, therefore theta equals 2k pi over 3. Now remember, we're trying to find the cube roots of 1, so we're really trying to find z. So remember, we solved the equation z cubed is 1, and z, all the z's will be the solution to this equation. We're expecting 3 solutions. So if z equals r cis theta is the general equation, the general form of the roots, well, we know that r is 1, and we know that theta is 2k pi on 3, where k is 0, 1, 2, 3, etc. So therefore, z is equal to 1. Remember, it's r cis theta. R is 1. Theta is 2k pi on 3. So z equals 1 cis 2k pi on 3. Again, where k is 0, 1, 2, 3, etc. Sorry, I'm just off screen. So therefore, z equals 1 cis 2k pi on 3, where k is 0, 1, 2, 3, etc. Okay. Now remember that we only have 3 solutions for z cubed is 1. So if I keep substituting in different values of k, what's going to happen is that after some time I'm going to get repeated values. So we just want the first 3 distinct values. So if we substitute, so when k equals 0, we get z is 1 cis. If k is 0, we get cis 0, which is, I'll just go down here, 1 cos 0 plus I sine 0. Now cos 0 we know is 1, sine 0 is 0, so we get 1. So when k is 1, we get z equals 1 cis 2 pi on 3, because k then is 1. So we get 1 cos 2 pi on 3 plus I sine 2 pi on 3, which is, now cos of 2 pi on 3, that's like cos 120, quadrant 2, cos is negative. The acute angle in that quadrant, if I just draw a quick 2 pi on 3, it's here. So I've got, that's 2 pi on 3. There's pi on 3 in there. Quadrant 2 cos is negative, but quadrant 2 sine is positive. We get 1 times a half. I don't need that 1. But sorry, it's negative. 1 times negative a half plus I times sine of 2 pi on 3. Sine of 60 is root 3 on 2. So plus I root 3 on 2. So therefore, it's negative a half plus root 3 on 2i. That's when k is 1. So that's one of, so we've got 2 of the roots so far. When k is 0, z is 1. That's one of the roots. When k is 1, z is negative a half plus root 3 on 2i. That's one of the second roots, or the second root. When k is 2, z equals 1 cis 4 pi on 3. Because k is 2, it's 2 times 2, which is 4 pi on 3. Now, with that, remember our arguments go between 0 to pi and 0 to negative pi, and 4 pi on 3 is over here. So we're going to, instead of calling that 4 pi on 3, we will call it negative 2 pi on 3, because remember our arguments go from 0 to pi or 0 to negative pi. So that's the same as cis minus 2 pi on 3, which is cos minus 2 pi on 3 plus I sine minus 2 pi on 3. Now cos in quadrant 4, again the related angle is pi on 3 in there. Cos in quadrant 3 is negative, so this will be negative 1/2 plus, now sine in quadrant 3 is negative, so it'll be plus negative root 3 on 2i. So therefore the third root is negative 1/2 minus root 3 on 2i. Now I'm going to draw these roots. Okay, so they're our three roots. Okay, I can call them Z1, Z2, Z3, as in the first root, second root, the third root. Okay, so actually I'm going to go over to the next page. So can you just turn over to the next page? You'll find a blank space at the top. Now if Z1, Z2 and Z3 are the cube roots of 1, we can sketch these, as I was saying, on an Argand diagram. Now if we do sketch those, I'm just going to write down what the roots were. Z1 was 1, Z2 was negative 1/2 plus root 3 on 2i, and Z3 was negative 1/2 minus root 3 on 2i. I'm going to sketch those on the Argand diagram. Sorry, I'm also going to write down what they were in mod arg form. This one was 1 cis 0. This was 1 cis 2 pi on 3. And the third root was 1 cis minus 2 pi on 3, remembering it was 1 cis 4 pi on 3, but we're writing it with the principal argument needs to be either between 0 and pi or 0 and minus pi. So just sketching those, if this is 1 unit, so 1 cis 0 is there. I'm going to call that my first root, so Z1. Z2 is 1 cis 2 pi on 3, so roughly about 120 degrees, so this will be pi on 3 in there. This is 2 pi on 3. Sorry, I need to draw this about there. That's my second unit, Z2, if this has got modulus 1, so that modulus is 1. And then the third root, if that's also roughly 2 pi on 3, angle there is minus 2 pi on 3, but the magnitude is 2 pi on 3. If this modulus is 1 unit as well, this would be Z3, which is this angle here is minus 2 pi on 3. And 2 pi on 3 and 2 pi on 3 is 4 pi on 3. Remember these related angles in here are pi on 3 and pi on 3. Notice this other angle between Z2 and Z3 is also 2 pi on 3. So basically what we've got are, there are the three roots. And if I draw them on an Argand diagram, and that's the center there, 0, there's Z1, Z2, Z3, each have modulus 1, length 1 unit. All of them are separated by an angle of 2 pi on 3 between each other. Now that's no coincidence. The reason is a circle is 2 pi radians, okay, or 360 degrees. So therefore the angle between the roots, notice, is equal to 2 pi divided by 3, because there are three roots equally spaced around the circle. Okay, so therefore Z1, Z2 and Z3 are the cube roots of 1. Now on an Argand diagram, the three complex roots will appear as the vertices of a triangle, which are equally spaced around the unit circle. Now a unit circle is a circle with radius 1 unit, or radius 1. Okay, so notice that each root has modulus equal to 1. And as I said over here, that the angles between the roots are, or is, 2 pi on 3. The other thing to notice, if you just look at the roots, that the roots are, they occur in conjugate pairs. So look at Z2 and Z3, negative 1/2 plus root 3 on 2i. Z3 is negative a half minus root 3 on 2i. They're conjugate pairs. But you might say Z1 doesn't have a conjugate pair, but it does, because 1 is, we'll write it over here. So notice that the roots occur in conjugate pairs. What we'll do, we'll just do, for example, Z3 is equal to the conjugate of Z2, because Z2 is negative a half plus root 3 on 2i. Z3 is negative a half minus root 3 on 2i. Z3 is the conjugate of Z2. And if you look at Z1, Z1 is 1, which is 1 plus 0i, which is the same as 1 minus 0i, which is the conjugate of Z1. So the roots do occur in conjugate pairs, okay? All right, that's the end of that first example. Now, I'm going to just use a purely graphical method just by looking at what we've done here and what we've noticed. Now, this was this solution to z cubed equals 1, what we did before, finding the cube roots of unity. In this example here, I'm just going to use the graphical method to find the fifth roots of unity. Okay, so similar method to just this without doing all that working out from before. So, if the cube roots of unity form the vertices of a triangle that are equally spaced around a circle, then the fifth roots, the fifth roots of unity will form vertices of a regular pentagon, which will be inscribed inside a unit circle. So I'll just pause the video and write that down. Five roots of unity will form the vertices of a regular pentagon inscribed in a circle. Now, each side will subtend an angle of, now if up here with the 3 roots it was 2 pi over 3, we're going to have an angle of 2 pi on 5. So 2 pi on 5 at the origin. So therefore the 5 roots of unity are, remember they're all going to have radius 1. Okay, so the 5 roots of unity are, Z1, my first root, will be 1 cis 0. Okay, Z2, the second root, will be 1 cis 2 pi on 5. Okay, now I'm going to draw them before I keep going. So if this is 1 unit, the next one, 2 pi on 5, would be about here. That's my second one. I want that same distance. Okay. Then my third one, another 2 pi on 5 units along, which would be 4 pi on 5, to be somewhere here. And then the next one, another 2 pi on 5 units along, would be probably around here. And then another one, another 2 pi on 5 units along, would be roughly about there. And if I join these points, I really should be doing these with a ruler and making them the same length and roughly correct angles. So we've got 2 pi on 5, another 2 pi on 5, another 2 pi on 5, 2 pi on 5 in here, and 2 pi on 5 there. If I join all these, I am supposed to get a regular pentagon. 1, 2, 3, done something wrong there. I meant to go there. 4, that's not 1. And 5. Sorry about that. Not the best looking pentagon, but I haven't drawn these angles exactly at 2 pi on 5. So Z3 will be 1. So if this is my Z1 there, there's Z2. There's Z3, which is 2 pi on 5, and another 2 pi on 5, which is cis 4 pi on 5. Z4 is down here, will be cis 6 pi on 5, but remember we're not supposed to go over 1 pi, so we'll call it 1 cis minus 4 pi on 5, because remember principal argument is between 0 and pi, or 0 and negative pi. And the last root, Z5, is 1 cis 8 pi on 5, but remember we're not, so 2, 4, 6, 8 pi on 5, but rather than that, call it that, because that's gone over pi, we'll name it as a negative angle, 1 cis negative 2 pi on 5. Now, notice again that the roots occur in conjugate pairs. So these star ones are conjugates, and these little triangle ones are conjugates. So note that the complex roots occur in conjugate pairs. So therefore, Z5 equals the conjugate of Z2. Now, if I write them out, that's 1. We can see that they're conjugates of each other here. Here's Z5. Okay, there's Z2. That might be something plus something I. This is an X value minus the same value I. Looking at Z3, that might be negative something plus something I. This is negative something minus something I. So the other complex conjugates are Z5, Z5 is the complex conjugate of Z2, and Z4, is the complex conjugate of Z3. Okay, remember complex conjugates are reflections in the x-axis, and Z5 is a reflection of Z2 in the x-axis, and Z4 is a reflection of Z3 in the x-axis. I actually haven't worked out their exact points. We'd need to put them into Cartesian form to be able to do that, okay? At the moment, these roots are in modulus argument form. Now, to solve z to the power of 6 equals negative 64. We're going to do this the same way we did example 1, okay? So with this one, we're not going to draw it, okay? So we're looking for the six roots. There will be 6 roots of negative 64. Now, if we let z equal r cis theta, then z to the power of 6 using de Moivre's theorem equals r to the power of 6 cis 6 theta. So I've written z to the power of 6 in mod arg form. I need to also write negative 64 in mod arg form. Now, to be able to do that, I need to draw a quick sketch of where negative 64 would be, and negative 64 on a number line would be there. And just having a look here, the argument of negative 64 is pi, okay? So negative 64 is 64 cis pi. Now, you might think, why is it that? Well, it's because the modulus is 64. We never have a negative modulus. All right, remember modulus is square root of x squared plus y squared. It'll always be positive, okay? So modulus is always positive. The argument, how do we get to this point negative 64? Starting from the positive x-axis, we rotate anti-clockwise pi degrees. So it's negative 64 is 64 cis pi. Now, I'm going to expand that. Cis pi means cos pi plus I sine pi. Now, just showing you that this will equal negative 64, if I just do a quick cos curve, now remember that's 2 pi, that's pi, and if I do a quick sine curve, that's 2 pi, which is 360, and that's pi, which is 180. What is the cos of pi? It's negative 1. And what is the sine of pi, or sine of 180, is 0. So you can see that negative 64 is 64 cis pi. Now, I'm going to call this one and this one equation 2. Okay, so therefore substituting both these, so if we've got that z to the power of 6 is negative 64, therefore I'm going to replace both equations with these. Therefore r to the power of 6, cis 6 theta equals 64 cis pi. Now, equating moduli and arguments. Equating the moduli, I've got r to the power of 6 equals 64. Therefore, r is the 6th root of 64, which is 2. Equating the arguments, I've got that 6 theta, I know that cis 6 theta equals cis pi, right? Cis pi. Therefore, 6 theta. See, when this is now sort of in general form, you're sort of writing, well, sort of like that. But all the possible values for 6 theta will be pi, plus any multiples of 2k pi, or any multiples of 2 pi. So we go that 6 theta is pi plus 2k pi, where k equals 0, 1, 2, 3, etc. So now dividing by 6, we get that theta is pi plus 2k pi all over 6, again where k is 0, 1, 2, 3. So therefore z, remember z is defined as r cis theta, therefore z is 2 times cis of pi, cis theta, theta is pi plus 2k pi over 6, where k is 0, 1, 2, 3, etc. Now, we know that we're going to have 6 roots, okay? So we're going to have to find the first 6 roots that are different to each other. So now we start by substituting. So when k is 0, we get that z, I'll call it z1, my first root. No reason, just it's the first root. z1 would be cis. Now, if k is 0, I get just pi on 6. Okay, now I'm going to, because that's an exact value, we're just going to work out the exact Cartesian, write it in Cartesian form. So that's 2 cos pi on 6 plus I sine pi on 6, which is 2 times, now cos of pi on 6 is cos 30, which is root 3 on 2, plus sine of 30 is a half, which is a half then times I, and this gives me root 3 plus I is my first root. Now, when k is 1, my second root will be 2 cis. Now, if k is 1, I get pi plus, and it's k is 1, I get pi plus 2 pi, that's 3 pi on 6. 3 pi on 6 is pi on 2, which is 2 cos of pi on 2 plus I sine pi on 2. Now, this is 2 times, now cos of pi on 2, that's my cos curve. Pi on 2 is cos 90, which is 0, and sine of 90 is 1. Okay, this is the sine curve. This is the cos curve. So, cos, this is 2 times cos 90, which is 2 times 0 is 0, and sine of 90 is 1, so it's times I, and therefore our root here is 2i. Next, when k is 2, this is my third root. Z3 is 2 times cis. Now if k is 2, I'll get 2 times 2, that's 4 pi plus 1 pi is 5 pi, so it's 5 pi on 6. So that's 2 cos 5 pi on 6 plus I sine 5 pi on 6, which is 2 times, now cos of 5 pi on 6, I'll just do a little sketch somewhere up here. So remember we had pi on 6, which was just there. 5 pi on 6 is here, there, 5 pi on 6, still the related angle, see this is 5 pi on 6. So cos is going to be negative and sine is going to be positive. The related angle is still 30 degrees. So we've got negative root 3 on 2 plus sine of, this is the same as sine 30 is a half I, which is negative root 3 plus I. Now notice, I'm just underlining root 3 plus I. Actually, no, don't notice anything yet. Nothing to notice. Just keep going. Next, when k is 3. Z4, which is Z sub 4, the fourth root, will be 2 cis. Now when k is 3, we will get 2 times 3 is 6 pi plus 1 pi, that's 7 pi on 6. But the problem is we don't want to leave it as 7 pi on 6. So this is 2. Now where is 7 pi on 6? It's over here. But that's the same as minus 5 pi on 6. Okay? So here's 7 pi on 6, which is the same as minus, so here, I'm saying that this will be on the angle 7 pi on 6. Related angle in here is pi on 6, same as minus 5 pi on 6. Okay, so basically the same values as these, but different depending on all stations to central. Now cos here is negative, so I've got 2 times negative root 3 on 2, but sine, sorry, I should just expand this. So 2 cos, sorry about this, minus 5 pi on 6 plus I sine minus 5 pi on 6, which is 2 times, this is cos minus 5 pi on 6. Cos minus 5 pi on 6 will be negative root 3 on 2, but sine of minus 5 pi on 6 is in quadrant 3, and that's negative as well, so minus a half I. So therefore, this fourth root is negative root 3 minus I. Now, notice, I'm just going to put this in a box, and this one in a box. Negative root 3 plus I was my third root. Negative root 3 minus I, they're conjugates of each other. Next one, when k is 4, we get z, the fifth root, is 2, 6. If k is 4, we get 8 pi, 9 pi on 6, which is 3 pi on 2. Now again, that is greater than pi. So 3 pi on 2 is there, which is the same as minus pi on 2. So it's 2 cis minus pi on 2, which is 2 times cos of minus pi on 2, plus I times sine of minus pi on 2, which is 2. Now the cos of minus pi on 2 and the sine of minus pi on 2. There's my cos curve. If I just extend it a little bit back, cos of minus pi on 2 will be here. That's 0. And sine of minus pi on 2 will be there, which is negative 1. So cos of minus pi on 2 is 0, and sine of minus pi on 2 will be negative 1, so it's minus I. And notice we get negative 2I. Now notice, in circles, I'm drawing this in circles, 2I is 0 plus 2I, minus 2I is 0 minus 2I, so the two complex roots that are circled are conjugate complex roots of each other. Now we've got 1, 2, 3, 4. If you want to take a guess, the last root should be root 3 minus I, okay, because this needs its conjugate pair as well. So let's look. So when k is 5, the sixth root is 2 cis. Now when k is 5, we get 10 pi, 11 pi on 6, but that's obviously going too far round. That is the same as 2 cis minus pi on 6, which is 2 cos minus pi on 6 plus 2 sine minus pi on 6. These are both in quadrant 4. So minus cos in quadrant 4, remember, is positive, so it's just the same as cos pi on 6. So that's the same as cos 30, which is root 3 on 2. And sine we know is, sorry, I shouldn't have this. I should have a bracket there. Okay, and a bracket here. And sine of minus pi on 6 will be negative, and it's negative a half. Sorry, I'm supposed to put an I there. That's what I did wrong. Which equals root 3 minus I. Now, that's what we were predicting. So we've got 6 roots, and they occur in conjugate complex pairs. Okay? So, no further solutions will exist, because what will happen is that if I put when k is 6, for example, I get 13 pi on 6, which is the same as pi on 6, coming back to the first one. So no further solutions exist. As I just said, substitutions of further values of k will lead to repetition of roots. Would repeat roots already found. And again, notice the following, that the first root Z1, or sorry, Z5, Z5, which is this one, or Z6, is the complex conjugate of Z1. So Z6 equals complex conjugate of Z1. Z5, the fifth root, is the complex conjugate of Z2. And Z4 is the complex conjugate. So this one, the fourth root, is the complex conjugate of Z3. Okay? Okay, so notice that, in other words, that the roots occur in conjugate pairs. Okay? Another example, use De Moivre's theorem to find in mod arg form the cube roots of -2 minus 2i. If you look at what we've been doing earlier, the complex number needs to be in mod arg form first, but our complex number is not in mod arg form, so let's write it in mod arg form first. So -2 minus 2i is down here. Okay, this is our complex number. Now, obviously, this angle here, well, this is going to be 45 there. So this is -3 pi on 4. Okay, so that's the argument of our complex number there. Well, that's Z. Well, that's what Z cubed is. It's actually not the complex number. So let's look at the modulus of this. Now, if we draw up a right angled triangle, that's 2 and that's 2. So the modulus of, well, this is what Z cubed equals. So I suppose I can call this, sorry, Z cubed. The modulus of our Z cubed is the square root of 2 squared plus 2 squared, which is the square root of 8, which is 2 root 2, or which is 2 to the power of 1.5, 2 to the power of 3 on 2, I'm going to write it as. And the argument of this Z cubed is, we can see here, -3 pi on 4. So therefore, I can write Z cubed, we know is -2 minus 2i, but I can write it as 2, I can write it as 2 root 2, it's not a problem, or I can write it, yeah, I can write it as 2 root 2, it's not a problem. It's 2 root 2, so Z cubed is 2 root 2 cis -3 pi on 4, okay? Now, we know as well that Z cubed is, if Z equals R cis theta, then Z cubed is R cubed cis 3 theta. So what I'm now going to do, I'm going to now equate, so therefore I can say that R cubed cis 3 theta equals 2 root 2 cis -3 pi on 4. So therefore, if R cubed is 2 root 2, therefore R is the cubed root of that. Remember, 2 root 2 is root 2 times root 2 times root 2, really, because 2 is root 2 times root 2. So if R cubed is 2 root 2 or root 8, then R will be root 2, okay? Or I could have said if R cubed is root 8, then R is the cubed root of 8. I'll just put it here, which is 2, okay? Now that's equating moduli. So equating, yeah, so equating moduli, we've got that. And equating arguments, we've got that 3 theta equals -3 pi on 4 plus 2k pi, where k equals 0, 1, 2, 3, and so on. Dividing by 3, we get that theta is minus pi on 4, because if I divide by 3, the 3 on 3 cancel, plus 2k pi over 3. Now working out what our roots are. So when k equals 0, my first root, my first root Z1 will equal root 2 cis. Now if k is 0, I just get cis minus pi on 4, which is root 2 cos minus pi on 4 plus I sine minus pi on 4. Sorry, going off screen. Now cos, that's cos of 45. So it's root 2 cos, and that's in quadrant 4, that would be 1 on root 2. Quadrant 4, sine of 45 is minus 1 on root 2i. And expanding those brackets, I would get 1 minus I. Sorry, they just wanted the roots in mod arc form, so I could just stay there. I could just write that Z1 is that, but I've done it in Cartesian form as well, so it doesn't matter. So Z2 will be root 2, when k is 1, Z2, the second root, would be, remember our it's r cis theta, so it would be root 2 cis. Now, if k is 1, we get 2 pi minus pi, but it's minus pi and 4, sorry, plus. I can write this as a common denominator if we want. So I will do that actually. So minus 3 pi plus 8k pi on 12 is theta with a common denominator of 12. So when k is 1, we get 8 minus 3, 5 pi on 12. Okay, so I'm not going to work out that one because that's not an exact value. Okay, so the first root is root 2 cis minus pi on 4. The second root is Z2 is root 2 cis 5 pi on 12. And when k equals 2, we get the third root will be root 2 cis. Now, when k is 2 here, we get 16 minus 3, that's 13 pi on 12, which remember, we can't write it as that, okay? 13 pi on 12 is just about there. That's 13 pi on 12, and that is the same as negative 11 pi on 12, okay? Which is root 2 cis negative 11 pi on 12. Okay, now, the other way of getting that, instead of letting k equal 2, so here I'm going where k is 0, 1, 2, it can be 0 plus or minus 1 plus or minus 2, because if I put k is negative 1, I will get this. So if k was negative 1, I'd get minus 8 pi minus 3 pi is minus 11 pi and 12. But look, you can do it either way, but you just got to watch for repeats of roots, okay? So they're your 3 roots. So therefore, your 3 roots are Z1 is root 2 cis minus pi on 4. Z2 is 1 minus I. And Z3 is cis minus 11 pi on 12. Notice, sorry, a bit messy. Notice that these roots are not complex conjugates of each other. But notice we didn't do cube roots of unity or fifth roots of unity or, you know, sixth roots of negative 64. We did the roots of a complex number. So, and we did not get that our roots were complex conjugates of each other. So now looking here, the nth, in summary, the nth roots of 1, that is the n roots of z to the power of 10, n equals 1, are equally spaced around the circumference of the circle with center 0, radius 1, separated by an angle of 2 pi on n at the center. One root will be 1. So one root is 1, is even, the other root will be at negative 1. So for example, if I looked at something like z to the power of 4 equals 1, we know one root would be 1. Remember, the others will be equally spaced around the circle, so there'll be one there, there'll be one up here, and one down there. So if there are 4 roots, they're separated by 2 pi on 4. Now we know that 1 to the power of 4 is 1, so there's one root, the other one would be here at I, the other one would be here at negative 1, and the other one would be at negative I if I was solving z to the power of 4 is 1. So if n is even, the other root will be at negative 1. Now the other roots occur as non-real conjugate pairs. Now the roots are, so the roots are 1 cis or cos 2k pi on n plus I sine 2k pi on n. where k is 0. You can do 1, 2, 3, or you can go k is 0 plus or minus 1 plus or minus 2, whatever, until the unique roots are identified. Now, the nth roots of any complex number are going to be a bit different. They will be equally spaced. So just in this example here, we had, if we sketch where these are, minus pi and 4, 1 minus I. So I'm just going to do a quick sketch up here for these ones. So minus pi and 4 is minus 45 there. 1, that's a bit of a weird one. One sec. It's not weird. I just wrote the wrong thing. That's still the first root. The second root was root 2 cis 5 pi and 12. So just putting that in. So the second root, so the first one was minus pi on 4. The second root is at 5 pi on 12, which is up here. And the third root is minus 11 pi on 12, which is there. Now, if we do the difference between those three, if we've got 5 pi, that's really 13 pi and 12. So that difference is 5 and 13. That's 7 pi and 12 separation. Just having a look there. No, 5, that's 8 pi and 12, sorry. 8 pi and 12. And the difference between this is minus, see, minus pi and 4 is minus 3 pi and 12. Difference between those as well is 8 pi and 12. Difference between minus 11 pi and 12 and minus 3 pi and 12 is a difference of 8 pi and 12. So these are separated by 8 pi on 12, okay, all the way round. So coming back down here, the nth, so this was the nth roots of 1, or some, yeah, of just like the number 1. But the nth roots of a complex number, like this example 4, right? Because it was solve z to the power of 3 equals negative 2 minus 2i. So it's z cubed is minus negative 2 minus 2i. That's the nth root of a complex number. They're usually, are equally spaced around the circumference of the circle with center 0. Radius will be nth root of r, and separated by an angle of, again, 2 pi n at the center, because 8, for example, in this example, 8/12 pi is 2/3 pi, 2 pi and 3, and that was for 3 roots in that example. So separated by an angle of 2 pi on n at the center. The roots will be nth root of r cos alpha plus 2k pi on n plus I sine, not much room, alpha plus 2k pi, all on n, where k is 0, plus or minus 1, plus or minus 2, etc., until all the unique roots are identified, and there will only be, if there is z to the power of 3, there'll be 3 roots, and so until the unique n roots are identified. Now, when investigating nth roots of complex numbers, the following factorization is useful. So w to the power of n minus 1 is w minus 1, notice 1 power less of w, 2 powers less of w, down to 1 power of w, 1 and no powers of w. We've seen this factorization before. W minus 1, this is difference of 2 cubes. That would be w squared plus w plus 1. This would be w minus 1, w4 plus w cubed plus w squared plus w plus 1. So that's just a useful factorization that you'll need to know.